All right, so last time we started 12.3, and we had taken a look at a few different things, and we were on at the point where I was going to show you how to think about some motion issues. So we're going to talk a little bit about equations of motion. So we're going to consider a projectile launched from an altitude h at an angle theta. We'll say an angle of elevation theta. With initial speed v sub 0. And the image you should have in your mind looks something like this. We're at a height, let me make this better, of h. All right, a height of h. Our initial velocity is v sub 0, and then this is our angle of elevation right here, theta. All right, so using Newton's second law of motion, and assuming the only force acting upon our object is gravity, then we have the following. So last time we talked about force equals mass times acceleration. And we're going to use the assuming part in this next statement right here. So our mass, or I'm sorry, our acceleration is only affected by gravity. And so the gravity is, of course, forcing it downward, not outward anywhere. So this is a j vector. And it's negative because it's going down instead of up with the gravity, right? And the derivative of velocity is acceleration. And our acceleration, again, is this negative effect of the gravity, or the effect of the gravity, which is a negative, times the 9.8. So the velocity then is the integral of this component, which would be negative g. I'll put the t here, and then our j vector is c1. So we just integrated. There was no variable t there to begin with, so now we've got the t in there. And we talked about this last time too. We're going to state it again here. In order to find C1, we need v of t, that is the velocity, for some value t. But we only know v sub 0. So using trig, did you guys have any idea how useful trig was when you took it? You used it a lot. Using trig, we can find that v of 0 is v of 0, I'll put this back in on my diagram in a minute, cosine theta v0 sine theta, which would then equal the C1 vector. So up here, back on that diagram, it's kind of small, so maybe I should make it a little bit larger. I'm looking at this triangle along the top. Hang on. So along the top, I've got this triangle. This side length is V0. Here's my theta. And then I can find the other two side lengths based on the theta and the V0, so that the value at the bottom is V0 cosine theta, and the side value is V0 sine theta. So that's where those are coming from, is from that particular triangle with trig. All right, so let me take this piece and I'll copy this to the next slide. We're going to continue from here. Okay, so now we're working back with v of t. So v of t we had said above was negative g of t, negative g times t, and then the j vector. So this same, and then plus c1. You know what, let me write that in here. I don't have it written there in my notes, but let me write that in there as a reminder since I switched slides. All right, so this was my initial, initial statement of what the vector for velocity was. And we want to put in there the C1. C1 is listed above here, of course, but we're going to put it in component-wise. So the first component of C1 is the V0 cosine theta. The second component is V0 sine theta, but that's the component that then is going to be added to the negative GT, because this is actually just 0 and then negative GT. Then if we're dealing with position, the position vector, which we've been calling r of t, would be the integral of this velocity vector. So we're going to do this again. So we're going to integrate here. So the first component doesn't have a t in it at all, so that we can write that simply as v0 cosine theta t. And then the second vector has a t in the second component, but not in the first. So the first component is going to be v0 sine theta t, and then the second component is negative, let me write that a little better, negative g t squared over 2. And then all of that needs to have something else added to it, another constant vector, right? So we'll call it C2 just so that it's identified differently than last time we called C1. So to solve for C2, we can use R of 0. So what is R of 0 in the context of my, I don't know if you want to say my picture or the situation or the context here, what is R 0 going to be? Can you tell?
0, like as a vector?
Well, it is a vector. It's a vector representing the height of my object at the beginning. So this t is at time 0, right?
I mean, like with both components, it's 0h.
Yes, 0h. Is that what you're asking me, is how you wanted me to represent it? Yes, that's correct. So this R0 component is 0h. Very good. So it's the initial height, or the initial time 0, and it's where I'm located, which is at a height of h. And then, of course, I haven't moved left or right from the axis, so I'm at 0. All right, so R of t then will be V0 cosine theta t, and then V0 sine of theta t. Sorry, there's an extra comma in there. And then minus g t squared over 2, and then plus h. So there's my position vector. I've got my velocity vector, and we're going to work through an actual problem next. And as we work through this, there's going to be some components that we're going to have to find based on the context of the situation. So does everybody have this final vector R of t written down? All right. Our question that we're going to work with is we're going to find the maximum altitude the horizontal range and the speed at impact of the following. V0 is 98, it's my initial velocity. My height at this problem is going to be 0, and my angle of elevation is pi over 6. Okay, we're going to start with the maximum altitude. Visually, what is this asking you to find? Maximum altitude. What does this mean in terms of the context of this problem?
It's the highest peak on its arc.
Right, so if you imagine something like a baseball being thrown or something like this is the tallest place where your object is going to be, right? So think about from Calculus 1. When you were finding a location like that, what were you doing? How did you find something like that? Yes. And what about the derivative did you need to know? When it was equal to 0, right? Maximum height is going to have a location where the derivative is equal to 0. All right, so just write yourself a note about that to start with here. So this has to do with finding a derivative equal to 0. That's how you find maximum altitude. Now that's going to find the t value for the maximum altitude, right? Now if you actually want to find the maximum altitude, then you have to evaluate at that particular t value that you found. Okay, so we want the, and in this case, we're dealing with a component. I mean, we've got components here, right? We don't have just a function. So what is it in our situation that we actually want to be 0? What piece of the derivative do we want to be 0? Can you imagine? We have kind of a two-dimensional picture going on, right? Our baseball, if you will, is going left and it's going up at the same time. Okay? Right. We want the vertical component to have a derivative of 0. We want the vertical component to change directions. Our horizontal component's not going to be 0 here. It's going to continue to go. It's just going to go downward now instead, but it's still going to be covering sort of distance on the ground, if you will. So we want our vertical component to be 0. And I said it a little funny, but I want the vertical component's derivative to be 0. So we need to find the derivative. And there was an equation that we were given that dealt with that. So let's start from what my acceleration, we can actually create these three vectors. The acceleration is negative 9.8 j hat, right? What is my velocity going to be? Well, we created equations that did this, right? Let me find that right here. Our equations had V0, and our V0 is 98. Cosine of theta, we'll evaluate the theta here in a little bit, times, where did I get it? No, I'm on the wrong line. And then the sine of the theta value minus 9.8t. And if we evaluate this, that is a v of t, not an r. Sorry, it almost looked like an r. And if we evaluate this at the pi over 6...
Are we wanting to plug in the pi over 6 here?
Yeah, we are. I was going to evaluate it here, but maybe I'll do it this way. That's good. Yeah, we're going to put in the pi over 6, yeah. I was going to do it in 2 separate steps. I don't know that I needed to do it that way. I didn't in my notes, but for some reason I felt like it for the moment. All right, cosine of pi over 6. Sine of, oh, I left this, I'm sorry, I left the 98 out here. There's a 98 in there too. 98 sine of pi over 6 minus 9.8t. All right, so what is the cosine of pi over 6? Right, square root 3 over 2, and then multiplied by my 98 gives me what? 49 square root 3, good. And then how about the sine of pi over 6? That's 1/2, so that's just going to give me a 49 here, yeah? And then I have minus my 9.8 t. Sorry, t. But what do we want? We want the vertical component, which is the second component, right? To do what? To be equal to 0. So we're going to set that equal to 0 to solve. All right, so 49 minus 9.8t equals 0. What t value does that give me? 5. 5 seconds. Okay. That doesn't quite tell me the maximum height. That tells me the time when it's going to give me a maximum height. So what am I going to do to find the maximum height? Yeah, plug it into what? The position function, which we haven't actually written out yet, right? So let's write our position function out, and then we'll be able to plug that in. So let me move my height statement down just a little bit here, and let's do position function. All right, so our position function, r of t, is the 49 point, I'm not 0.3, square root 3, t, and then it's I hat, and then the 49t minus 4.9 t squared j hat. If you take a look back at the equations that we created, so I promise I'll come back to this slide in just a second, but if you take a look back at the equations we created for r of t compared to v of t, they have the same components except that at the very end we've got the integral and then these have the t's attached. So there's no reason to start from scratch here. I'm going to have the same coefficient of 49 square root 3 and 49 in there. So these match here and here. And then I've got this one squared and divided by 2. All right, so there's my position equation. Plus I had a C1 here, or C2, whatever you want to call it. But that piece is going to be pretty easy to deal with. That piece is going to be equal to 0. The reason I know that is because I was told that my initial height was 0, right? So there, in a very real way, there's a 0 back here, so I don't have to deal with that. Okay. So there's my position equation. So just like James said, we're going to evaluate this position equation at 5 seconds. So this is 49 square root of 3 times 5, I. Plus 49 times, I'm sorry, not plus. Oh, I know what's wrong. It's just the j component, right? It's just the height. We don't care the distance along the x, we're just dealing with the height component. So r of 5, let me see. All right, let me write it out, and then I'll put in what I want. This piece right here is my height. So that's the piece I care about evaluating. The other piece is inconsequential to the question. All right, so what happens when we plug in 5 into the 49? Times 5 minus 4.9, that's a point, times 5 squared. What do you get for the maximum altitude?
Did you divide it by 2? Oh, you already did that, sorry.
Yeah, it was 9.8 originally, and so now it's 4.9. Yep, we already did it.
Sorry.
It's okay. 122.5. Mm-hmm. And I think our problem was given, it didn't say. I think the standard for what these are working with is in meters. This height doesn't say meters because it was 0, but it is in meters. All right, so we've got 122.5. That's my maximum altitude. All right, the next thing that it asked me to find was the horizontal range, and the last one was speed of impact. So those are related concepts, the idea being that eventually what comes up must come down, and it is going to hit the ground again from where it started. So how are we going to figure out, of course, the horizontal range is how far it goes along the horizontal. We did the vertical range basically by finding the maximum altitude. How am I going to find the horizontal range? What do I need to do?
Well, because it took 5 seconds for it to reach the maximum, it takes another 5 seconds for it to hit the ground, so t is going to be equal to 10.
That's true. So this is going to happen, so my horizontal range, so my image is that it's doing something like this. This is the picture you should have in your mind. So if it took it 5 seconds to get to here, that's not a horizontal distance, but that's the time length that took us to get there, then you're exactly right. It's going to take 5 seconds to get beyond that as well. And of course, there's other ways of verifying or justifying that, but you're correct. So to find the horizontal range, I can simply find out what is my horizontal component at t equal to 10, right? And I found the horizontal component before. It was 49 square root of 3 times t. So I can do that at time 10. So this will be 49 square root of 3 times 10 to give me what?
490 squared.
Okay, 490 square root of 3. Can you give it to me with decimals instead? If we're dealing with an actual distance, it makes more sense to give the answer in decimal expression at the very end. 848 what?
0.7.
Okay. Meters. So the horizontal distance that we're going to cover, the horizontal range, is 848.7 meters. What about speed of impact? Okay, what t value?
10 seconds.
10, because 10 is when it hits the ground.
And then take.
So this is asking us, in essence, I'm going to write down what you guys are saying, to evaluate what? What am I going to evaluate?
The velocity vector.
The velocity vector
And then we have to take the magnitude of it.
at t equal to 10, right? And then we're going to find the magnitude. And that's actually what we talked about in terms of what speed means last time, is it's the magnitude of velocity. So that's why we're finding the magnitude at the end. So is everybody okay with processing the question and why it's asking us to do this? Okay? All right. So we're going to evaluate the velocity vector at t equal to 10. I had one of those once upon a time. What was the velocity vector? And we can do it without the sine and cosine thetas in there because we evaluated it already at our theta, so we can use those pieces. So I can actually use the 49 square root of 3 And then what was the other one? 49?
Minus 10.
Okay, is that okay? All right, and then we're going to evaluate that, like you said, at time 10. So I have 49 square root of 3. And then I have 49 minus 98. What's that, negative 49? And then we're going to find the magnitude. So I have 49 square root of 3 squared plus negative 49 squared. Square a couple things, add them together in square root. What do you have? What's that? My magnitude, oh, you're right, it should say 10 here. Thank you. Yes. Did you get a value?
98.
98, yep. Meters per second for velocity.
Oh, that makes
Yes, it does. All right, any questions?
we got that a lot.
Huh?
I said we could got that a lot easier.
All right. Let me write the homework down. Did I write the homework down for this one last time? I don't think I did. Not 277, 777. 2, 4, 7, 10, 12, 15, 18, 20, 21, 23, and 26. There we go.